Okay, so day 7, oscillators 2 is for today. Yesterday we went over some very basic oscillator circuits and got a little bit of understanding of how oscillators work and how you can get oscillators in a number of different ways of doing it. Okay, so in the next course, after we finish this course, we will be going into digital electronics and studying digital circuits. Now, digital circuits are all about timing. They are timing circuits. They have to be extremely accurate because what we're doing is transferring data that's time dependent. Okay, so we were talking essentially translating zeros and ones very accurately. If we miss a 0 or a 1, the whole thing busts. It ends and has to restart, and you have to start from the very beginning. So you can't let that happen. So you need to do that very accurately. The main thing that you need is a very good timing circuit. Timing is all about timing. So we need to get something that's a lot more accurate than some of the systems that we talked about yesterday. We can do that using a piezoelectric material, which has been used sometime. The first time we started using those is to do electronic clocks that we have on our wrist. Okay, they keep a certain periodicity to it, a very definite period. Okay, the piezoelectric material is basically a crystal material. Okay, and it's got some oxygen and some other metal. It's a metal oxide, and it's because it's a crystal material. It's ionic in nature, so the ions themselves have a positive charge and a negative charge. And so if you disrupt the construction of these, and you can displace the positive from the negative, you essentially build up an electric field. Okay, so we can do that by pushing on it, by putting a pressure on the piezoelectric material, either a positive pressure or a negative pressure. In other words, we can compress it or we can expand it. If we compress it, we create a positive displacement. And the other way, we get a negative displacement, a negative charge, and so forth. So we basically create an electric field. So that we do that, the distance of the crystal, the thickness of it is going to tell you at what the frequency, the natural frequency of that crystal is. Every solid piece of material has a natural frequency, a frequency that it naturally responds to. In other words, it resonates. It's a resonator. Okay, so everything has a specific frequency that it resonates at. And the thickness, in the case of a piezoelectric material, the thickness of that determines what the frequency is of that, of the natural frequency of that particular crystal, the way it's made. And that is extremely accurate because it's very, very thin. It's the distances are atomic level distances. Okay. That's why it's so accurate. So we use those crystal oscillators to give us a timing that is extremely accurate. And so we'll start the chapter with the uh, piezoelectric materials, and then we'll add them to uh, a lot of the oscillator circuits to make them even more accurate. Okay, and so we're going to discuss first piezoelectric materials and then the oscillators that use those things.